Hi, with this video I want to do a few more comparisons of order and moment stationarity, just try to build a little more intuition about these conditions and how they relate to each other. Okay, so first of all is kind of how does order and moment stationarity relate to each other. So first note here on the slide is that if we're jth order stationary, then we're first order stationary, second order stationary, up to j minus 1 order stationary, right? So let's go just look at the previous slide to think that over. Right? So if I'm jth order stationary, I've got this condition that this kind of joint distribution for j sets of points in time, that probability density function is unchanging to shifts in time. And so if that's true, then any lower order distribution must also be unchanging in time, right? So for example, this kind of j pairs of time joint distribution, if that's unchanging to shifts in time, then certainly this kind of marginal density function at a single point in time must be unchanging to shifts in time. Okay, so anything lower order, all we've done is integrate out some of the random variables, and so we couldn't kind of introduce a time changing component by that integration out. Okay, so order stationary is kind of nested, that any lower order stationarity is ensured. Moment stationary, it's not the case. So we don't necessarily, if we're second moment stationary, it's not guaranteed that we're going to be first moment stationary. However, jth order stationarity implies jth moment stationarity. So we could think about that and just maybe with a couple quick notes, right? So if we think about second order stationary, that means that kind of a pairwise joint distribution. So x at time t1, x at time t2, evaluated at u1, u2, is equal to a joint distribution at x at time t1 plus r, x at time t2 plus r, u1, u2. All right, so that'd be the second order. Second moment, pull this up a little bit. Right, that means that the expected value of x at time t1, x at time t2 is equal to the expected value of x at time t1 plus r, x at time t2 plus r. Right? If those expectations are equal, then we're second moment stationary. But those expectations that we're computing here, in order to compute that expectation, with the integral form, we're going to take, u1 and a u2, and then we're going to multiply that by the joint probability density function for x at time t1 and x at time t2, and we're just going to complete an integral. So this expectation depends only on this integral, and this expectation on the right-hand side depends only on the integral of the PDF on the right-hand side. So if these two PDFs are equal to each other, these expectations are going to have to be equal to each other as well. Right? And so that's why we can guarantee jth moment stationarity if we have jth order stationarity. Okay. So here's a question to think about: is do we have a ranking of stationarity? So if I said I have a process with first order stationarity, and I have a process with second moment stationarity, is there one of these that's stronger than the other? And you could pause your video and think about it for a second. Okay, so let's think it over here. So if I've got first order stationarity, we could think over what that implies. Right? So we could say, right, so that's that the marginal PDF is invariant to a shift in time. Okay. And so if I think about expectations, what expectations are going to be constant by that? So the expected value of x of t is going to be constant. Let's see if I can do this. Give myself a little more room here. Right, so any shifts in time on this expectation of x of t, that's going to be unchanged because this marginal PDF is unchanged. Similarly, I could look at like the expected value of x of t squared, right? That would still be constant because it still just depends on that PDF to the left. Expected value of x of t cubed, that's constant. And so on, right? So I could raise x of t to any power. Those expectations depend only on this marginal PDF to the left, and so they would all be constant. Let's look at second moment stationarity then in terms of those conditions. So second moment stationarity so here we're looking at the expected value of x of t times x of x at time s, and that has to be equal to x at time t plus r multiplied by x at time t plus s plus r. All right, and so that's constant. But this expectation is at two different points in time, and I can't guarantee in this first order stationarity that the expectation of the product of the x at two different points in time is constant because I don't have any constraint on the joint probability density functions at 2 points in time. I only have this kind of marginal probability density function constraint. So in the end, neither of those conditions is stronger. Because they address different properties. Okay. So maybe a borderline trick question at the top of the slide, but I like to think through questions like that just to kind of solidify our thinking about how these different characteristics relate to each other. Okay? And then to summarize this all, I build the kind of following table in my mind of how these stationarity conditions relate to each other. So let's make a column of order stationarity, and make a column of moment stationarity. Okay. And then we could think about, say, first order stationarity and first moment stationarity. Okay. So if we have this condition of first order stationarity, and if I have a process and I can check that box that it's first order stationary, then that ensures that it's first moment stationary. Right? So first order stationarity implies first moment stationarity. Okay. And we saw that, let's see, like, well, I did the example for second, but it's true for jth order and jth moment stationarity. So order stationarity always implies moment stationarity at the same level. Okay. So let's fill in our example, I guess, of the second. So second order stationarity implies second moment stationarity. That was the example we did a couple slides back. Okay. And so on. So we could go to third. We could go down to jth. And then we can go down to, let's go down to infinite at the bottom. So mathematically, we could have this infinite dimensional joint probability density function. And that would give us, if that was unchanging to shifts in time, that would give us infinite order stationarity. Okay? And each of these cases implies the corresponding level of moment stationarity. Okay. So the left column always implies the right column at the same level of row. Okay. And there's some other relationships we can build in here, though, as well, based on the hierarchy of order stationarity. Let me clean up this arrow here. It's a little messy. And then let's go back. Okay. So we said that if x of t is jth order stationary, then it's also first order stationary, second order stationary, up to j minus 1 order stationary. So because those are dealing with kind of lower order joint probability density functions, and we can get those by just integrating out the variables we're not interested in, then second order stationarity implies first order stationarity. And third order stationarity implies second order, which then implies first order stationarity. So higher order stationarity always implies lower order stationarity. Okay. We can't draw the same arrows on the right-hand side. The higher moment stationarity doesn't necessarily imply lower moment stationarity. It's commonly the case, but it's not mathematically guaranteed. Okay, so the strongest condition I can get to is kind of infinite order stationarity, and that'll imply kind of all lower orders are stationary, and it'll imply that all moments are stationary, because all of the rows to the right will be implied by all of the rows to the left. Excuse me. And so you can see that for whatever condition I can get to an order stationarity, everything above and everything to the right will be also stationary. If I have a condition of moment stationarity, that doesn't necessarily imply that other moments or other orders are stationary. So those are going to be kind of less broadly implying stationarity of other characteristics. Okay, so that's kind of the relationships between stationarity. And then in terms of our shorthand notation, let's come back and think about that for just a second. So we talked a few slides back that if we're mean and second moment stationary, and remember mean is first order stationary, sorry, first moment stationary, and second moment stationary, we call that weakly stationary. And then if all moments are stationary, we have strict stationarity. Okay? So let's draw those on. So if I've got the condition that the first and second moments are stationary, this blue box here, if I can check all the boxes in here, I have weakly stationary, a weakly stationary process. So that's a condition that we'll think about sometimes. And then if I have all of my moments stationary, that's fine. This black box is strictly stationary. So those are a couple conditions that are going to be useful for us. All right, and then we can see if I have a second order stationary process, I by implication have a weakly stationary process, because the moment stationarity is going to be ensured by that. And if I have an infinite order stationary process, I'm guaranteed to have a strictly stationary process as well, because of this chain of relationships. So that's a way to think through the hierarchical nature of these stationarity characteristics. Okay, so that is stationarity, and we'll stop this video here.